So now we are backing up to section 7.3. We're going to look at interval estimates here for the population mean. And it turns out we have to use a different distribution to do that. So let's start with a problem that we'd like to solve. So a police officer sets up a stakeout in a 35 mile per hour zone, randomly selects 10 drivers, and records their driving speed. So here's the data. And then we want to find a point estimate, find and interpret a 99% confidence interval, and then residents in the area have complained that all the drivers speed on that road. Is it possible that drivers go the speed limit and we just had an unusual sample? So in order to do this, we need to develop our confidence interval formula. So confidence interval for population mean is going to have the form point estimate plus or minus a margin of error, just like we did for proportions. We need that margin of error. So recall that the X-bar distribution is going to be approximately normal if the population is normal or n greater than or equal 30. So either one of those give a normal population, give a normal sampling distribution. The mean of the X-bar distribution is mu. The standard deviation of the X-bar distribution is sigma over root n. So we want to know, is this interval going to be point estimate plus or minus margin of error, which is X bar would be our point estimate, estimates the population mean. And then can we use Z alpha over 2 times sigma X bar? So before we did Z alpha over 2 times sigma P hat. So if we do, that'd be Z alpha over 2 sigma over square root of n. Well, almost. Turns out that the shape of the X-bar distribution depends on the shape of the population, or n. So the X-bar distribution, it may not be normal if the population is not and n is too small. So the solution is that we're going to require that the population is approximately normal or n greater than or equal 30. So that'll be a requirement for a test. Second problem, population standard deviation sigma is almost never known. And the sample standard deviation S is often not a good approximation, again, if n is small. So the solution to this problem is instead of using standard normal statistic, X bar minus mu over sigma X bar, we are going to use a new statistic called the T statistic. So X bar minus mu divided by S over root n. So it's called the student's T statistic. So the difference is that we're using the sample standard deviation here when the population standard deviation is not known. So the T distribution is compensating for not knowing population standard deviation. So we first need to find out how to get these T values here on the calculator. So let's look at some properties of this T distribution. So the T statistic has a sampling distribution that has the following properties. It's mound-shaped, symmetric, mean is 0, and then the variability of the distribution here depends on the sample size n. And the variability decreases as n increases. So this ends up giving better results than using the Z distribution for confidence intervals. And we express that dependence by saying that the T value has n minus 1 degrees of freedom, and we'll write that as df equals n minus 1. So degrees of freedom are 1 less than the sample size. So here's what this T distribution looks like. If T is, if degrees of freedom are 4, that means sample size is 5. Then this is mound shape, but it's got a lot more area out in the tail, so more variation. And then, for example, the T distribution with degrees of freedom is 20. You can see that dashed line there. It's more mound shaped, and in fact, it's closer to the normal distribution. Here's the normal distribution in the solid black line. So we're going to define this T alpha over 2, which is what we're going to use in place of Z alpha over 2, to be the T value with area alpha over 2 to the right for given degrees of freedom. And we can find that on the calculator by doing second variables and then inverse T instead of inverse Z. And you'll put in your left area and then your degrees of freedom. So notice that 1 minus alpha over 2 is the left area. So for example, if we want to compute t.025 for a sample size of 10 and then sample size of 30, so t.025, that's going to be over here on the right-hand side. And the area to the right of that value is 0.025. And then the left area will be 0.975. So if n equals 10, then our t.025, we're going to do inverse t. And then we put in our left area, which is 0.975. And then our degrees of freedom, 9, 1 less than the sample size. So let's go ahead and compute that. So second variables, go to the distribution menu, inverse t number 4. So our area, that's left area, 0.975. Degrees of freedom, 9. 2.262. And then for n equals 30, we do the same thing, except degrees of freedom are 29. So this will be inverse t, 0.975, 29. Compute that real quick. So second variables, go to inverse t, and we just have to change our degrees of freedom to 29, 2.045. So I'm including an extra decimal place there. A lot of times I'll use only 2 decimal places. So then with this t-distribution, then our confidence interval has the form x bar plus or minus t alpha over 2 instead of z alpha over 2 times sigma x bar. So t alpha over 2 s over root n, that is our margin of error. Now here we can write an expanded form. This is our shorthand notation. Here's the interval in expanded form. So note, if sigma is known, if we do know it, we can just use the z distribution and sigma over root n, but that almost never happens. And then also your confidence interval requirements here. We have to have a sample that is randomly selected from target population, and then the population is approximately normal or n greater than or equal 30. So we mentioned those up above. And then we can use calculator shortcut here using stat test t interval in order to find this. So now let's go ahead and go back to that first example and we can finish up.